Previously, we've looked into what happens if x approaches a certain number and the values of f of x increase or decrease without bound. This time, let's look at another point of view. What happens now here as x increases without bound, or x approaches positive infinity? As you can see here, as x approaches positive infinity, this time it goes that way. The values of x, the values of f of x rather gets closer and closer to this line here. For example, let's say we have this point here. Its x value is this, while its y value would be here. It gets pretty, I know the line is not that straight, but it gets closer and closer to the x-axis, which would have a y value rather of 0. So as x approaches positive infinity, it will reach a certain number. Or as x approaches positive infinity, f of x would approach a certain number, in this case 0. If you're going to look at the other side here, as x approaches negative infinity, it's the same. For example, for this point here, its x value is this, but its y value also gets closer and closer to 0. So with that in mind, this is now what's happening as we have limits at infinity. A while in the previous video, we're talking about infinite limits. The limit is at infinity. This time, what happens now if if x rather is the one at infinity? So we have limits at infinity. Oops, sorry. We have this one here. There you go. So, this is the formal definition with epsilon delta. Now, what we need to remember is this theorem here, that if r is a positive rational number, and since it's any real number, then the limit of c over x raised to r as x approaches positive infinity would be equal to 0. Now, if x raised to r is defined if whenever x is less than 0, that happens in certain cases, then as x approaches negative infinity, that would also be equal to 0. So, with these two theorems, we can now look into the limit of functions as x approaches positive infinity or negative infinity. Let's take a look at number 1 here. For number 1, there you go. We have the limit of 5 minus 2 over x squared as x approaches positive infinity. From limit theorems, we know that this is the same as the limit of 5 as x approaches positive infinity minus the limit of 2 over x squared as x approaches positive infinity. The limit of any constant as x approaches any number is the constant itself. This is still equal to 5. Minus, in this case, we follow now this theorem here. As x approaches positive infinity, c over x raised to r, the limit of that would be equal to 0. So therefore, the limit of this would be equal to 0. And this is 5 minus 0 is equal to 0. Therefore, the limit of 5 minus 2 over x squared as x approaches positive infinity would be equal to 5. Now, what happens if we would have givens like this in the rational expressions form? We would have to apply a technique following a technique, we're going to have a technique that this will come out from our given expression. So for example, in number 2, in number 2, we'll have the limit of 2x minus 1 over x plus 1 as x approaches negative infinity. The technique goes like this. First, check what is the highest degree in the expression. In this case, that is 1. And in 1 over x, it is defined as x approaches negative infinity. as we recall in our previous, in the one that we explained a while ago, as x approaches negative infinity at 1 over x, it's also approaching 0. So therefore, we can find a meaning for this. We can look for this expression. Or at least we can find the limit of x approaches negative infinity because it's defined at 1 over x. So using this, we would now have to multiply this expression by 1 over x over 1 over x. This is equal to 1, so technically this expression times 1 is the same. But with that in mind, we are now going to have expressions in the numerator and the denominator that will follow our theorem. So in doing so, this becomes the limit as x approaches negative infinity of, that becomes 2x times this, that's 2x over x, minus 1 over x times negative 1, that's minus 1 over x, all over, this becomes x over x, and this becomes plus 1 over x. If we are to simplify things, we're going to now have the limit as x approaches negative infinity of 2 minus 1 over x over 1 plus 1 over x. And if we apply the limits, the limit of a constant is constant, so that's 2. The limit of this as x approaches negative infinity based on our theorem is 0. The limit of a constant 1 as x approaches negative infinity is 1. While the limit of this as x approaches negative infinity is 0. Simplifying this, this becomes 2. Therefore, the limit of 2x minus 1 over x plus 1 as x approaches negative infinity equals 2. Now let's have number 3. We have, I will write it here to save space. We have the limit of 3x minus 2 over the square root of 2x squared plus 1 as x approaches negative infinity. Now, if we're going to check what is the highest degree following the technique we use in number 2, the first usual answer would be 2. However, we have to bear in mind that there is a square root in the denominator. So the powers would actually be x and then square root of x squared, which is technically x. So the highest degree is still 1. Therefore, the first thing to think is that we'll use 1 over x. However, in the denominator, we have this. So most probably what we would have to use is 1 over square root of x squared, especially in the denominator. In the numerator, we can use 1 over x. We just have one caution here. This is at negative infinity, and this is the expression we're going to use in the denominator. If you recall, in solving equations, for example, y is equal to x squared, if we get the square roots of this, the square root of y would be equal to positive or negative x. And that would have an effect in our 1 over square root of x squared. Now, since this is negative infinity, we would have to use this negative x. Hence, we would need to write this as negative 1 over square root of x squared. Because we are approaching negative infinity and we have a negative 1 over x squared. Therefore, this will then be equal to the limit as x approaches negative infinity of 3. Let's write first it in this form. 3x minus 2 over the square root of 2x squared plus 1 times negative 1 over square root of x squared over negative 1 over square root of x squared. Let's pull this one up. There you go. This will then be equal to the limit as x approaches negative infinity of. We multiply this becomes negative 3 over square root of x squared plus 2 over square root of x squared all over. This will become here the square root negative square root of 2x plus 1 over square root of x squared. Now, applying our algebra here, on the numerator, we can simply simplify our denominator. So we'll have the limit as x approaches negative infinity of negative 3 over x plus 2 over x all over. Now, here at this part here, this is negative here outside, but since these are radicals, we can combine them into the square root of 2x squared plus 1 over x squared. That's possible because by the quotient law of exponents and square root is technically an exponent of 1/2, we can combine them. So our denominator will simply become the limit as x approaches negative infinity. Our numerator remains the same, just like this. Sorry, there should be an x here, right? There should be an x here. So when we simplify this, sorry, this should have been just simply, wait a minute, let's fix this. When we simplify, this should have just been, let's write first negative 3x over x here. So when we simplify here, simplify further here, I'm going to have negative 3 only, plus 2 over x all over, this is negative, square root of, that's 2x squared over x squared plus 1 over x squared. So from here, let's fix first again our denominator. We have the limit as x approaches negative infinity of negative 3 plus 2 over x all over negative. We have the square root of this gets cancelled, so that's the square root of 2 plus 1 over x squared. So, alright, before we continue here at this point, I would just like to clarify something as I was looking at the solution and it seems I made a mistake somewhere. Here. Wait a moment. Okay, so I guess the mistake I made here is that since this is only applicable for the square root, there should technically no negative sign here in the numerator. Now, I know that will cause a confusion because this should be the same so that we multiply it to negative 1. However, this is a special case because this is a square root. So here on top, let's correct that. This should have been still positive and this should still have been negative. Following this one here. So this one on top, let's make these corrections. So again, the reason why we're correcting this is because the negative, we have x is equal to negative square root of x squared. This one only is applicable since we have a negative square root. We have a square root rather. And that's not applicable on the numerator because it's just 3x minus 2. So remember, technically before, when we do this, we separate the two functions to analyze their limits. So in 3x minus 2, it doesn't matter. It simply needs to be 1 over x without the negative. Without that negative. So now proceeding from here, this becomes, applying this limit here, we have 3 minus 0 over negative square root of 2 plus 0, which would end up having negative 3 over square root of 2 or negative 3 square root of 2 over 2. Again, let me emphasize again the mistake that happened here, that here in 3x minus 2, there should not have been a negative, because that negative is applicable only at the square root part, since this is coming from negative infinity. Therefore, the limit of 3x minus 2 over the square root of 2x squared plus 1 as x approaches negative infinity will be equal to negative 3 square root of 2 over 2. Now, if we combine both the as x approaches infinity and f of x approaches infinity, we have what we call infinite limits at infinity. And this can be seen in polynomial functions. So let's try to graph our polynomial functions. Oops. I think it's better if we're going to graph 2. So let me graph 1 here. Then another one here. Why? If we would have the functions f of x is equal to cx raised to n, where c is positive, then most probably it will look like this if n is odd, and then something like this if n is even. Oops, let's write it in there. N is even. So as you can see here, as x tend to approach positive infinity, the values increase without bounds. So f of x also approach positive infinity. In this case here, as x approach negative infinity here, their values tend to go down. F of x approaches negative infinity if n is odd. On the other hand here, if n is even, as x approaches positive infinity, we get more values from there. Oops. There you go. And the f of x values tends to approach positive infinity. And even here on the other side, as x tends to approach negative infinity, their values still go up to positive infinity. This is the application of infinite limits at infinity, the end behavior of polynomial functions. So going back to our definition, we get this definition here saying that the limit of x raised to n as x approaches positive infinity would always be positive infinity. As you can see at these two examples, this is positive infinity, this is positive infinity. And the limit of x raised to n as x approaches negative infinity is positive infinity if n is even, as we can see here, and it will become negative infinity if n is odd, as we can see here. Now, c is assumed to be positive here because if c becomes negative, this gets flipped, and we apply our rules a while ago the rules before, rather, at infinite limits. Also, we have our theorem here that states that if you have a long polynomial, all you need to do is get the limit of the leading term, and that becomes the limit of the entire polynomial. Here, we have some examples. We have the limit of 4 x raised to 5 as x approaches positive infinity. So based on our previous theorem, if it's positive infinity, regardless of whichever n is, it's positive infinity. So automatically, the limit of this function is positive infinity. Once it becomes negative infinity, that's the time we have to check. If n is odd, it becomes negative infinity. Since 5 is odd, therefore the limit of this function as x approaches negative infinity is negative infinity. Further, it was mentioned a while ago that if we have a polynomial, we only need to get the limit of the leading term, the one with the highest exponent. Hence, this would be equal to the limit of 7x raised to 5 as x approaches positive infinity. Hence, this is 5 and this is positive infinity. This is automatically equal to positive infinity. Now, our application of the limits at infinity would be our horizontal asymptote. We are told that the line y equals b is a horizontal asymptote of the function f if at least one of the following statements would be true. Now, here, we are asked to find the horizontal asymptote of the graph for the following functions. The thing here is that in vertical asymptotes, we first find c, then we check if it's really an asymptote using limits. If for horizontal asymptotes, it's the other way around. You use limits to find what is the horizontal asymptote. For example, in number 1, we have, let's write f of x is equal to 2x squared over x squared plus 1. So, to find the horizontal asymptote, we have to find the limit of 2x squared over x squared plus 1 as x approaches, if we look at our definition, positive or negative infinity. We just need actually 1, so let's first use positive infinity. so that we don't get any complications with negative infinity, especially if there is a square root. So following our technique a while ago, we get the highest exponent, which is 2. Therefore, we multiply this with 1 over x squared over 1 over x squared. This then becomes the limit as x approaches positive infinity of 2x squared over x squared all over x squared over x squared plus 1 over x squared. Simplifying, we get the limit of 2 over 1 plus 1 over x squared. That's as x approaches positive infinity. Applying the limits, we get 2 over 1 plus 0, which would add up to 2. Therefore, the limit of 2x squared as x approaches positive infinity equals 2x squared over x squared plus 1. Therefore, with this, the line y equals 2 is a horizontal asymptote of f, because this has been shown to be 2. So let's take a look. Let's move down a little bit and let's go to number 2. We have f of x is equal to x plus 1 over x cubed minus 1. There. So let's now look for the horizontal asymptote of this function. Let's now look for the limit of x plus 1 over x cubed minus 1 as x approaches positive infinity. With this, we have the highest exponent as 3. So the highest degree is 3. Therefore, we multiply the expression by 1 over x cubed over 1 over x cubed. Hence, we're going to get the limit as x approaches positive infinity of x over x cubed plus 1 over x cubed all over x cubed over x cubed minus 1 over x cubed. Hence, we simplify the fractions. In the complex fraction, we get the limit of 1 over x squared plus 1 over x cubed all over 1 minus 1 over x cubed as x approaches positive infinity. Applying the limit, we're going to get 0 plus 0 over 1 minus 0, which will end up at 0. Therefore, the limit of x plus 1 over x squared minus 3 as x approaches positive infinity is equal to 0, making the line y equals 0, or the x-axis, a horizontal asymptote of the function of f in 2. So for number 3, let me write it just before I scroll down. Number 3, f of x is equal to x to the 4th over x squared. So scroll down for more space. There you go. So now we have to find the limit of x to the 4th over x squared plus 2 as x approaches positive infinity. So the highest exponent is 4. Hence, we multiply by 1 over x to the 4th over 1 over x to the 4th our function. This becomes the limit as x approaches positive infinity of x to the 4th over x to the 4th all over x squared over x to the 4th plus 2 over x to the 4th. Simplifying things, we get the limit as x approaches positive infinity of 1 over 1 over x squared plus 2 over x to the 4th. Applying the limit, we do get 1 over 0 plus 0. And this is undefined, which makes the limit not existing. Therefore, the limit of x to the 4th over x squared plus 2 as x approaches positive infinity does not exist. But actually, we can try to double check. Before we declared it doesn't exist, let's check if we're going to get an infinite limit for this. So checking, since this is 1 over 0, we get 1 over x squared plus 2 over x to the 4th as x approaches positive infinity. Now, if we place really large numbers here, since this is squared and this is to the 4th, it will still remain positive or greater than 0. Hence, with a positive number with this greater than 0, the limit is actually at positive infinity. So therefore, the limit of x to the fourth over x squared plus 2 as x approaches positive infinity is actually at positive infinity, which we cannot say as a horizontal line. Therefore, there is no horizontal asymptote for number 3. Now, the limit process is what we use to secure the horizontal asymptote. However, we would have a shortcut here. There you go. So, we say, if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. And the line y equals 0 becomes the horizontal asymptote, which is what happened in number 2. The degree of the numerator is less than the degree of the denominator. That's why we were able to see that the limit is equal to 0. So y equals 0 is the horizontal asymptote. Here, if the degrees of both the numerator and denominator are equal, then the limit of the rational function is the ratio of the leading coefficients. Ratio of the leading coefficients. Since these are both 2, that's 2 over 1, which is equal to 2. That's why the limit, as we compute, is equal to 2. If the degree of the numerator is greater than the degree of the denominator, like number 3, degree of the numerator is degree of the denominator, the limit of the rational function does not exist because it's at infinity. Sorry, at infinity. Therefore, there's no horizontal asymptote. So you can use this as a guide, as a shortcut for finding limits at infinity and for looking for horizontal asymptotes. Because once you use this, you can now verify using limits if it's actually true. So that's about limits at infinity, infinite limits at infinity, and horizontal asymptotes.